So to introduce myself, I'm Stephen McAuley. I'm a technical lead at Ubisoft Montreal, and I'm sort of the lucky guy standing up here today with a speaker's badge that gets to talk to you about all the cool rendering stuff we did. But really, we have a big team at Ubisoft Montreal, and a game like Far Cry 4 is so big that it's a real team effort. So I'm going to try and make sure that I call out all the guys who worked on all the features I'm going to talk about today. So I joined Ubisoft to work on Far Cry 3, and this is a game that came out in 2012. It was really great. We actually found that loads of people liked it. It got a 90% Metacritic score. And when you're working on a game that's the game design is really fun and you have a really cool gameplay loop, it's pretty awesome when you get the chance to make a kind of a sequel and do Far Cry 4 based on that. So it's really cool as a graphics team as well. We were able to stick with a lot of the same people. So we knew the strengths of our engine and our weaknesses, and we knew exactly what we wanted to do to improve the engine. And it's obviously some of these improvements I'm going to go through today. So Far Cry 4, if you don't know much about it, it's an open-world first-person shooter. World about 10K by 10K. It's pretty big. We have a day-night cycle, as you'd expect for an open-world game. And with anything that's kind of dynamic time of day, as a graphics programmer, there's kind of really no hiding place. And we're set in Kyrat, which is a kind of country based upon Nepal. We had cross-platform and cross-generation development, so we shipped for 5 platforms at a time, which is pretty tough. I mean, our mandate as a graphics team was to lead on kind of current gen on Xbox One and PlayStation 4, and trying to keep the last gen version the same as what we shipped on Far Cry 3, because it did a really good job. It kind of gave us a lot of constraints, because we had to keep the last gen version kind of running, which kind of affected a lot of our decisions throughout the project. And at the end of the project, as was kind of inevitable, like when we had to go back and optimize a few little bits about the PS3 and the 360. But in the end, that kind of meant we had a better product than FC3 on all platforms. But really, given our mandate as a graphics team was to develop new features for the new consoles, I'm really going to talk exclusively about that kind of work, but I might throw a few tidbits in about the PS3 and 360 along the way. So kind of what areas did we improve? Well, we kind of looked at 5 areas. So materials, lighting, vegetation, and anti-aliasing, and terrain. So I'm going to cover the first 4 today. I'm not going to talk about terrain, because hopefully you were all in Ka Chen's excellent talk just beforehand in the opposite room. And he talked about the virtual texturing work he developed. And if you didn't see it, make sure you go and check out the slides. It was really awesome work. So let's get started with materials. On Far Cry 3, I did a talk at SIGGRAPH 2012 talking about how we did some physically-based shading stuff. We kind of had glossiness and reflectivity material parameters, and we only had monochrome specular. As a bit of a side rant, I've kind of noticed nowadays this kind of definition of physically based keeps kind of changing. Like what I kind of considered physically based back in 2012 is now the old way of doing things, and physically based now means layered material editors and other fancy things. So maybe we should just talk about more and less physically based. It might be a bit more accurate kind of term. Anyway, so the goal from Far Cry 3 was that we wanted to improve the appearance of our metals, because we only had this monochrome specular reflectance. Kind of didn't look very good. We couldn't get colored specular. And if you look at something like the kind of concept art for a place like Nepal, you'll see loads of gold and kind of bronze that we really wanted to bring out. And also in a first-person shooter, you'll find that your weapons cover quite a large portion of the screen. So you can get your weapons looking really nice. You have at least part of the screen that's going to look pretty awesome. So look, like everybody else, we looked at the Disney model. Nothing too original here. We took the anisotropic GGX BRDF and corresponding Smith geometry term, and just used a standard Lambertian diffuse. We didn't look at kind of other diffuse models, such as the Disney model, but really, I really struggle to see it's worth the cost at this moment in time, though, yeah, we'll keep looking. And we ended up with kind of 4 parameters in this 0 to 1 range. Again, really important, keep all your parameters in 0 to 1 for kind of artist intuitivity. So we have glossiness, reflectance, metallic, and anisotropy. So Disney call reflectance specular, and they call glossiness roughness, or inverse glossiness roughness. We stuck with glossiness for legacy reasons, for keep the Far Cry 3 kind of naming the same. And really what I'm going to go across is just go into that bit into how we did that anisotropy, and how we did like the metallic. So Looks like a metallic parameter. Hopefully you all know about this by now. So it's pretty simple. So if you have this single float value that you can blend for your specular reflectance, you just blend from a monochrome value to your kind of diffuse albedo, which really is then a kind of a specular albedo. At the same time, you blend out your diffuse albedo to make sure you get no diffuse lighting and lots of cool colored specular lighting. Simple, and it works really, really great. Because what it means is you just need a single channel in your G buffer for colored specular, rather than having to store a whole other kind of 3 colored terms. And actually, this is great, because we could use this feature then for the old-gen consoles as well, which got rid of the specular reflectance, fixed it as 0.03, and replaced the value in the G buffer with a metallic instead. If you do this approach, though, you do need to give your artist a little bit of training. Because behave your kind of diffuse textures, which are no longer diffuse, really, it kind of changes with that use of the metallic value. And it can be a little bit confusing for people. Like, you kind of notice you're developing, say, a weapon, and you've got like a metal a knife blade and you know, like a, say, wooden handle. We'll find in the texture the wood looks quite dark, but the metals are all going to be really quite high in that range. So your artist might kind of want to kind of adjust them and kind of make them closer together. But we gave them some good Photoshop color swatches to make sure they kind of didn't do that and had some good guidelines. And you know, after a couple of weeks, they really caught on pretty well and they did some awesome kind of work. We also introduced anisotropy to get cool brush metals and also for certain types of cloth. So see how the anisotropy parameter increases there across those spheres. So let's look at the anisotropic GGX distribution formula, which is kind of long and confusing. And this is a bit scary, because if we actually break this down, and we look at what we have to store in our G buffer, well, we need 2 glossiness terms, plus a normal, tangent, and binormal. And that's really confusing then, because we have to pack a full tangent space into the G buffer, and yeah, like, that's going to take a lot of values, we think. But actually, we can actually borrow some ideas from animation programmers. And they wrote some interesting papers from Crytek and also Nicholas Frickom on the BitSquid blog about storing tangent space as a quaternion. And they've kind of mastered the packing kind of for this. They want to get animation down nice and small. So what we're going to store, we're going to store a quaternion 10, 10, 10, 2. We're going to store the 3 smallest components, and they're in the range -1/√2 to 1/√2, because if they're any bigger, they would be the biggest component. So we just need to do that, and that's great, because we can just pack those into 0 to 1 range, and we get more precision. And we also store in that W component the index of the component we've dropped, the 0, 1, 2, or 3. You might be thinking, well, can't you just get away with it with storing X, Y, and Z in, say, 11, 11, 10, getting a bit more precision out, and reconstructing the W? Well, it turns out it doesn't work. You kind of lose a lot of precision, so you really need to actually drop this biggest component and reconstruct that one. And that turns out it's not too bad. You can kind of find the biggest component. It's actually only 5 instructions if you use some kind of GCM-specific tricks. So kind of like a major axis problem. So you already actually have the cube map face ID instruction where you can just use that to get the major axis out of the X, Y, and Z, and then max 3 to quickly help you get to whether the W is any bigger. And I'll put all the code for packing and unpacking quaternions in a G buffer in the appendix to these slides. So you can go check all that out later when I release the slides next week. What's the quality like? Well, I kind of worked out it's about quality equivalent to about a naive packing of normals in 888. You do get a bit of faceting on smooth surfaces, and we're kind of lucky on Far Cry. We don't really have that many smooth surfaces. But if your game is kind of like that, you might want to look again. I mean, overall, I mean, the problems you're going to get problems again, what I said, the quality of the normals, they could be a bit higher. I do think there's a bit more research to be done here, whether we can use those 10 bits a bit better to distribute the kind of values better, to get precision where it's needed. You also can only store orthonormal tangent space. Now, that's not actually so bad, because actually we don't have orthonormal tangent space for our normal maps in Far Cry. But what we construct for the anisotropic shading is orthonormal. So you can kind of make those 2 different tangent spaces, and it actually works out okay. It might be a problem if you want to do something like lean mapping, which is kind of our initial plan, but we weren't, so that's okay. Obviously, we'd like to make the speed of the packing and unpacking a little bit quicker, but you know, it never really came up much in our profiling once we optimized it. The main problem really we had was how to blend decals, because obviously now once you're doing something like a quaternion, you can't just do some simple alpha blending. So we only supported 1 layer of decals, and that was an art kind of restriction, and we had to kind of read back the current normal quaternion buffer and then reconstruct things from that. What's cool, though, is actually how they worked well is with the virtual textures, because all our decals on the terrain were stored in a virtual texturing, so it wasn't actually a problem for us at all on that. It was only on kind of buildings. So it's kind of a nice thing about two different techniques working together, and if our game was all like virtual textured, it kind of meant this problem went away for us. For reflections, well, it's a little bit trickier. We'd love to do importance sampling or something into a QMap to get some awesome results, but we can't. So I'm kind of really grateful, actually, to it was Matt Patino who brought Don Reevy's article, and I think a GPU Pro 1 or 2, to my attention, about doing some like anisotropy and deferred shading. And he just did a simple trick to distort the reflection vector in a different direction. And actually, it's not perfect, but it looks pretty good. So, on the left, you've got no anisotropy. In the middle is kind of what we had originally, where we had this anisotropic highlight and an isotropic reflection, which is a bit kind of broken. And then on the right, we have what happens when you actually do this little trick for the anisotropic reflection. Again, it's kind of not perfect, but it's kind of a hell of a lot better than doing nothing at all. I really like showing pictures of these knives. I think our weapons team did an awesome job, and you know what? They use anisotropy everywhere. They loved it. And it's kind of really interesting because it solved a problem we had on Far Cry 3, where these guys, this weapons team, they keep coming up to us and say, we really want some fake specular on our weapons. And we kind of say, no, 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 we want to be physically based, no fake specular at all. And then we gave them this anisotropy, and that complaint just completely went away. They always felt they saw some glint or some kind of like something interesting going on in the weapons. So it's going to make perhaps this fake specular they wanted after all was actually just brushed metal. That's actually what they were looking at. And now we've kind of replicated the real world a little bit better. We've supported a wider range of materials. They can get what they want. So next topic is going to be our lighting. So there's kind of three improvements we wanted to make. The first was kind of our sky occlusion system. We wanted to kind of increase the resolution of that, and the system Jeremy Moore worked on. We also had our environment maps, where we wanted to make sure that they could dealt better with time of day changes. That's something developed by Gabriel Lassonde. And finally, we looked at the indirect lighting. We wanted to kind of extend our range beyond this kind of loading ring we have, so further out to that far in the distance. And we wanted a faster update as well from Far Cry 3 to prevent flickering errors. So let's start with our sky lighting model. Well, we used the Bruneton sky model and the Pretum sun model. This is something that actually developed by Assassin's Creed Unity that we managed to take, and it worked really well for us. We kind of really liked it. And once you've got the sky model, we just need to generate the lighting in third-order spherical harmonics. So that's pretty cool. So what happened in Far Cry 3 was that we had stored our sky lighting in light probes along with our indirect lighting. Problem is, the indirect lighting was kind of based on probes spaced at 8 meters, which is quite low resolution, and we thought, hey, GI is kind of a bit of a difficult problem to solve, so hey, why don't we just increase the sky resolution? That's something we can definitely do. So we decided to separate out our kind of sky lighting, direct sky lighting, from the indirect lighting. And we did something, the simple trick I think a lot of games have done, like Assassin's Creed, I think CryEngine has it in. We have this just top-down sky occlusion map generated from a height field over the kind of entire scene. And we make sure we actually generate visibility and second-order spherical harmonics from this height field. So the height field is kind of rendered on demand. It's not something we stream in. So our world is split into 64 by 64 meter sectors, and whenever a sector becomes visible, we're just going to render the height field of that. It's really, really quick. It means we have no streaming cost. And it means we get quite a high resolution as well of 25 centimeters per texel. And we kind of blur this then from before we generate the SH visibility. I mean, the visibility is kind of quite simple to do. Let's just take an SSAO kind of style approach. We just need to sample our kind of blurred height field with a rotated Poisson disk, store the proportion of the visible samples, actually just sum the directions of the visible samples then to get the directionality out. Once we've got that, we've got the direction and we've got the visibility. We just need to convert that into spherical harmonics. So what we're going to do is just create a spherical cap based upon the kind of the up normal, and we're just going to rotate into the direction that we need. So how do we apply this? Well, what we're going to do in the deferred lighting, we're going to sample this kind of SH sky occlusion texture. We're going to do some tricks. Obviously, this is kind of 2D, and we actually need to kind of modify things based upon our height above the terrain. So remember, recall, we have actually a blurred height field. So if something at the terrain height, we can have this use full SH occlusion. And then as we blend up to something in the height of the blurred height field, well, we're just going to kind of fade out to something fully visible. Gives us something that looks kind of 3D. Then once we have the primary visibility direction from SH, we can just construct a bent normal out of that. And we just need to then to sample our second order SH visibility and the third order SH skylighting in this bent normal direction and just multiply them together. And we did look at using SH product here, but we kind of found it was a bit low res, I think, in the end. So just here's some code, quick code to bending the normal. So you just need to get the primary direction out, scale it based upon the kind of the zeroth band of the SH, and then add that into our existing normal and renormalize. So let's look at some pictures. So this is kind of a scene without sky occlusion. I mean, even so, I think it shows some nice stuff with having like kind of cool skylighting, right? Because you've got look at the buildings, you can see different kind of shades on different faces. Here's how it happens if you add the sky occlusion in. Everything starts looking a lot better. It's still perfect. I mean, you can notice we actually have quite a harsh fall off, and that was actually art directed. We had a few tweaks in there to get it looking for how art direction wanted. And what's really cool is when we added the bent normals in as well. And what you might see, if you look, say, around the building, just drawing between the building and the ground, obviously you can see very disparate lighting. And yeah, the bent normals in, it really softens that out. So, something like that. Doesn't look quite as good on the big screen as it does on the monitor. So look at the slides later and you'll see, but I'll do that again. So, yeah, just kind of gives a little bit of softness, a little bit unifies everything a little bit more in the scene. And art direction really liked that because they felt that things, sometimes where the buildings join the ground, just they felt that things didn't look quite right. So environment maps. So let's ask ourselves this question. So how can we get a single cube map to have the right intensity at every single time of day? Well, one idea, of course, is why don't we just relight our cube map every frame? So what we need to do that? Well, relighting is something we're kind of good at doing. We kind of store G buffers in our deferred lighting. So why don't we do something like that for our cube maps, where what we'll do, we're going to bake offline cube maps and store, instead of a fully lit kind of thing, we're going to store a G buffer. We're going to store our albedo, and we're going to store a normal. Then what we need to do in our kind of frame, we're going to insert those along with a kind of a real-time generated sky texture to fill in those black albedo pixels. And we insert that into a lighting pass, light based upon our sun and our sky lighting. Then we need to take that and do our pre-filtering so we can have the BRDF, GRGX, BRDF match built in there. And then we're going to get a final relit key map as a result. So how do we do the lighting? Well, we do our sun and sky lighting without any shadowing or occlusion, because this would require a depth buffer. We decided to kind of save the memory. I think in the future, we'd probably want to add that depth buffer back in so we can get world position out, and I think it would definitely help improve things. We also get the indirect lighting from the nearest probe, and we normalize everything again with the luminance of the ambient term. On Far Cry 3, we were normalizing our Q maps by the kind of the color of the ambient. It turned out actually that introduced loads of kind of banding and color distortion, and just normalizing with the luminance works a lot better. So here's the results. What's really cool, obviously we have a real-time sky. There's no clouds in there, but you could have some fancy clouds moving. But you can see the sun moving across the sky. You can see that kind of in the mountains there in the distance. You can see how the lighting's shifting on those. And of course, obviously, you can see how the ground changes lighting at different times. Obviously, though, we need to talk about the filtering, because it's really important we do this. So what we're going to need to do for successive MIP levels, we need to sample our GGX distribution and do some importance sampling. Just on its own, it's a little bit kind of slow. It's really, really key to use the filtered importance sampling that was done in GPU Gems 2. It turned out that I think Seb Lagarde and Charles Deroussier at DICE had the same idea, and they kind of talked about this before me at SIGGRAPH last year. We came up with the same thing. It's the right thing to do. I found it's really important to match your QMAP faces together in your compute paths for better occupancy. Obviously, if you're doing a 4x4 QMAP face and you're sending that individually to the GPU, you're going to have a lot of wasted performance. And also, if your hardware supports it, it's really cool you can batch MIP levels together as well. Then you're going to really fill the GPU up with work. Turned out that this all was actually pretty quick. Filtering results. There you go. It works. So yeah, really, really quick. So we had 128 by 128 QMaps with HDR QMaps. Lighting, again, really quick. MIP generation, quick. Filtering, a little bit slower, but still really, really reasonable. We were bandwidth bound here. David Cook from Microsoft has kind of suggested that we look at using kind of R11, G11, B10 formats that might help speed things up. That's true. If we can deal with that for the precision issues, and I hope these times will go down a lot further as well. So indirect lighting, our third kind of lighting improvement that we wanted to make for Far Cry 4. So we have started off with a really cool system. If you were at GDC 3 years ago, you might have seen Nikolai Stefanov and Mikhail Gilbert talk about deferred radiance transfer volumes that they developed for Far Cry 3. So these were light probes placed at various points in the scene that stored radiance transfer information. When we came to looking at what we wanted to do for this system, we had a number of goals. Again, with this limitation of being this kind of cross-generational game, we decided, right, we actually want to stick with the same light probe set for kind of last gen and current gen. We really wanted to extend the range of the indirect lighting out, because in Far Cry 3, it was kind of stuck at around, I don't know, 64 meters around the camera, and we really wanted that to go further, because you could really see that kind of destroying. I really wanted to have faster updates as well by moving all the CPU work onto the GPU. So here's an overview of what we do. So offline, we're going to bake some probes. And we're going to bake this. They're going to store radiance transfer information in second order SH. So that's going to be 3 4x4 matrices. On the CPU, we're going to stream this probe data in. We're going to upload it to the GPU, and we're going to update our kind of page table. And on the GPU, we just need to calculate our radiance transfer, and then we're going to inject our probes into the clip map and sample the deferred lighting. So I'm going to step through some of these in a little more detail. So our world, as I said before, was split into 64 by 64 meter sectors. And probes are stored in cells. In each cell, we have a grid of 8 by 8 probes. So we're going to bake our highest level data, so just the first top level of the probes, where we have 1 sector per cell. And then we're going to generate MIPs from that. So we have MIP data, 5 levels of MIP data. So what's in a cell? Well, it's a radiance transfer probe list. So it's 64 probes, again, in this 8 by 8 regular grid. We also need to store our SH probe list as well. So this is going to be the final probes after they've gone through the radiance transfer, they've gone through this kind of relighting process. We just store that as well, and that's done once per frame. I also need to store the dimensions of the cell. So what MIP level are we? What size is it? Where are you in the world? And obviously, once we've got all these cells, the thing is, we can't have these kind of buffers stored individually in GPU memory. We can't have like a buffer put just one structured buffer for radiance transfer probes per cell. Again, it's not going to be really slow because you're working on small sets of data. What we need to do is kind of virtualization to have one big list. So that's what we're going to do. We're going to allocate this big fixed size list of cells, and we're going to break that into a fixed number of cells allocated for each MIP. So in our case, we have 80 cells in total, 5 MIP levels, and that's 16 cells per MIP. As worth saying, along using the virtual buffer stuff here, we're not using any PRT hardware, so don't worry about that. It's all done in software. So as a cell is streamed in on the CPU, well, if a free cell is available for that MIP level on the GPU, well, we're just going to allocate. Well, if no cell is available, then we just need to discard a more distant cell. Then, as a cell is streamed out on the CPU, well, we just need to mark the cell as free on the GPU. So it's pretty simple. And what's cool, because we have this big, long virtual buffer list, we now can perform like the radiance transfer all at once, really fill up the GPU. It's really, really quick. So just insert our sunlight and our skylight, take the list, and output some SH probes at the end. And these are the final probes we're going to use for lighting. So let's talk a bit about our page table. So each MIP level actually has a page table. And these are kind of spatially indexed in a 2D grid on the XY plane. And this kind of page table covers the entire world. What we're going to do on the CPU, we have all these page tables MIP per MIP, and we're just going to combine them into one, kind of filling in all the gaps. So in the end, we have this kind of page table which contains all the data for every cell in the world. And so the final page table is 160 by 160 sectors at the highest MIP resolution. And what do you need to do if you want to sample a light probe? Well, what we need to do, we just need to sample into the page table to find our index into the cell list. So what cell are we currently, is our lighting data currently stored at? We don't care what MIP level that is. From the cell, once we know what cell we're in, well, we can calculate from our world position what probe index in that cell we need to look at, and we just need to fetch the probe. Now, that's great and all, but obviously that's not going to have any filtering, especially not between MIP levels and not between individual probes, so it's not too great. And it's actually quite slow to do that lookup for every pixel on the screen, so we don't want to do that. So what we're going to do instead, we're actually going to inject our probes into a 32 by 32 by 5 clip map. So that's like a 32 by 32 texture array, 5 array levels, and obviously the same size because the 32 by 32 is covering a larger area in the world. And these are centered about the camera, and the 3 of these textures so we can store the 12 SH coefficients we need. So to sample, in the end of the day, we just need to find what cascade our pixel is in. We need to calculate the UVs for that pixel for cascades, the current cascade and also the next level cascade down. And we can sample both of them and just blend together based upon the distance. So let's look at kind of what performance we kind of have. So memory is pretty low, obviously. The page table is 25 kilobytes. Total cell memory is about 640K. And you're probably thinking, well, so you're doing a next-gen game, we've got all these massive load gigs of data to use. Why is your memory so low? Well, again, as I said, we're sharing data sets between kind of current gen and like last gen. So actually what happened here, we actually managed to optimize our last gen memory a lot. Actually, on a lighting system, I think we saved 2 megabytes or so in total across the last gen consoles. So obviously people were very, very happy about that. Performance, again, radiance transfer is really, really quick. And so is our injection into the clip map. And the full screen pass here, the full screen pass is actually what does our skylighting, so all the sky occlusion stuff I showed you earlier, applying the third order SH skylighting and sampling the clip map and getting the indirect lighting out. And we store that in a separate buffer. And that's read in the final deferred lighting pass. So what's great about this, we solved all our problems from Far Cry 3. We had faster updates because now we had no kind of CPU, GPU synchronization. It was all going to be done on the GPU, all the radiance transfer, rather than before. We had a much larger indirect lighting range because now we had all these MIP levels of the lighting data. We could go all the way into the distance. And we had a lot lower memory requirements, which, as I just said, was awesome for our last-gen consoles. Obviously, this has quite a few quality issues. So we have low frequency lighting, like every 8 by 8 meters are kind of at best. And also temporally as well, because kind of second order SH spherical harmonics and radiance transfer, it doesn't really pick up enough data. And also finally, we don't have our local lights kind of taken into account. So these are things obviously we want to look at and kind of improve for the future. So vegetation. Now, vegetation was actually one area that we decided to completely redo for next-gen consoles, given it's a really important part of our Far Cry game. So I want to give credit to Philippe Gagnon and Jean-Sébastien Gay for working on this system. And again, it was a completely different data set for our kind of current-gen and last-gen builds. So really, we did 2 completely different sets of trees. Our goals of developing this new system were, well, we wanted to improve our visual fidelity up close, and when you get really close to trees. We wanted to get improved lodding in imposters, as those kind of trees then go further away. And we wanted to get some cool simulation, a physics simulation done. So to explain what I'm talking about, well, vegetation can mean quite a few things. We've got trees, bushes, grass. Really, our new system only touched kind of these trees and these bushes. We didn't really look at the grass at all. So what we're going to do, we're going to create our trees using SpeedTree, and we're going to import them into the engine. We're not going to use anything like the SpeedTree runtime. We're just going to take the mesh data generated and import that in a format that we like. And how we built a tree consisted of this. A tree consists of a trunk and these leaf clusters. And once you have a lot of leaf clusters and put them on a trunk, we get a tree. And these are all kind of lodded individually. And we have 3 lods for the trunks and 3 lods for the leaf clusters before a tree becomes an imposter. What's really cool is how we do the leaf cluster lodding. What we're actually going to do, we're going to generate when we want to switch lods offline, and we can calculate the percentage of each leaf cluster visible from 12 distances and 9 viewpoints around the camera, around the tree. So let's take a look at this. So let's look in the left-hand image. This is how many you're looking at a tree. The red is going to be your kind of lod 0 clusters. The green is going to be your lod 1, and your blue is going to be your lod 2. And then if you kind of move the camera around to fix the kind of culling camera, and you're going to sneak a look around the side on the right-hand image, what you're able to see is that obviously the clusters closest to the camera are on the highest lod, and as they get further away, more and more occluded by the clusters in front, so they're going to be using a lower lods. And obviously, of course, as the tree moves into the distance, everything's going to turn blue here, and you're going to have the lowest lod in total before everything goes to an imposter. Simulation. So we have all our physics and movement of the tree simulated on GPU. What we do there, we have instance bones transformed into world space bones. So what's going to happen is we have a model bone list of all the models in the scene. and obviously a list of all our instances, tree instances in the scene. They're going to go into a computer shaded simulation, and we're going to spit out a much longer list then of all the wall space bones for every tree, which goes into our vertex shader. And this is great because it allows some really cool physics effects. So this is the first point where I try to play a video. So you can see where you're flying a buzzer, and it comes down, and you can see all the trees moving individually. You see the bushes reacting to the buzzer, and you can see all the grass waving as well. For the grass, you actually applied some kind of cheap water-like simulation to get that going as well. And this is really cool. Not many games, I think, have this kind of effects. So that's great for close to the camera. What happens when we get far away? Well, we want some cool things to generate some good imposters. And what we're actually going to do, we're going to take screenshots of 9 viewpoints around the camera, 8 perpendicular to the tree and 1 top down. So when we have an imposter, we can easily blend, depending on our view angle, what the tree should look like. But we're going to go further than that. Because actually what we're going to do is take G-buffer kind of screenshots. We want to capture the albedo, the normals, and the material properties. And that gives us a lot of textures for a tree. And again, we're not going to stop there. We're going to add even more. We're going to add this kind of depth billboard effect. So we want to capture low-res depth data as well during our G-buffer pass. And when we render our billboards, they're actually tessellated into a 16 by 16 grid. And we're going to displace our vertices depending according to the original tree depth. Fortunately, these screenshots aren't so great, but this is the front view on the left, and the side view is the same tree. As you can see, all the depth applied. I've been told this actually really helps a lot when a tree is lit from the side, and also when 2 tree imposters intersect. So that gives a much better blending between them. So it's worth doing this technique. And I'll give a few benefits later as well, as I'll explain. Ambient occlusion, standard thing everyone did, AO volumes. You've all seen this before. But it definitely gets a benefit to our tree lighting. And let's give some scary-looking vertex numbers. So for our rosewood tree on the right, we might see 170,000 vertices for like the leaves. It's worth noticing here, because we have our loading system, we're never going to render that many. It's only going to be like 80,000 max for that, because of the loading that we do, which allows us to have this kind of high detail. Of course, it's also probably fair to say that I'm not going to let artists make a tree like that again. And performance is actually pretty good as well. Our tree simulation, again, on compute is like really, really quick. And given for this scene, there's a lot of trees on the scene, have shadows about a millisecond, G-buffer about 5.5, rendering all this kind of alpha test geometry. It's pretty good. But obviously, we like to optimize because trees are always expensive for everybody, everywhere. Visually, however, I think vegetation is a really tricky thing to get right, because there's loads of things we're not simulating, and like bounces between blades of grass or the light scattering between leaves. What's really great is when you have some really cool technical artists who can kind of come in at the end of the project and just kind of do a few little cool tweaks to get things looking cool. I'm going to share a few of those with you. So one they wanted is a kind of a per leaf cluster random color tint. So this is an example. The first color is green, the second color is red, and we just generate tints varying between those two randomly. Really simple, really effective. And this is a bit of an extreme example, but it's not too different to trees you might see in Vermont in the autumn. We also really need to give imposters to life, bring imposters to life, because we had all this cool simulation up front, but then when we did imposters, they looked a bit flat and boring. So what are we going to do? Well, we just simulate some branch motion first by doing some per vertex sine waves. This is great, because we have those tessellated billboards, actually the vertices are going to move and the trees are going to shift a bit. We just simulated them by smooth triangle waves, as they did for Crytek many years ago. And we're also going to add some per pixel noise as well from a texture to simulate leaf motion. So you have the branch motion from these big kind of distortions, and then this little per pixel noise to fake this leaf motion. Worked really well. Again, I'm going to play this video. Hopefully you'll be able to see the difference between the noise on and the noise off. But if not, again, take a look offline. That's working pretty well. I think you can see that things look obviously a lot more dynamic when the noise is on. our kind of final topic of improvement today is anti-aliasing. Now, I hope you all saw Michal Jobot's talk at SIGGRAPH last year, where he went into a big overview of all the anti-aliasing techniques we tried. So really all the credit to this work goes to Michal, and also all the difficult questions at the end, please. Yeah. So what I'm actually going to present here is a strip down of that talk, and I'm going to talk about the things what we actually finally shipped with. So really, this high-res reconstruction anti-aliasing is looking at about kind of 3 different techniques that we're going to apply together to get a good anti-aliasing result. So the first is edge anti-aliasing. So this is pretty self-explanatory. You all know what this is what MSAs try to deal with when you have these edges in your image. You also need to look at temporal anti-aliasing as well, because the images move in time, so you've got this kind of third dimension we need to think about. And finally, we have temporal supersampling. So obviously, supersampling is when we take a big image and we're going to downsample it to something smaller. We like to do that temporally, where we take different samples on alternate frames and use that to combine this bigger image that we're downsampling. So there's a bit of an overview of kind of how things are going to work, and I'm going to go through this in a bit more detail. So you start with our current frame. It's going to go into our edge anti-aliasing. That feeds in, along with our previous frame, into the temporal supersampling and temporal anti-aliasing shader, which outputs our final frame. And that then goes back, fed in again, our frame n-1, and our accumulation history buffer gets fed back in again to do all that final temporal supersampling and temporal anti-aliasing for the next frame. So edge anti-aliasing. Well, we tried a lot of techniques. So we looked at analytic edge anti-aliasing for edge alpha-tested geometry. We also really wanted to, what we really wanted to do was the coverage reconstruction anti-aliasing that Michal presented at SIGGRAPH. And this gave us by far the best performance, but we had a lot of content issues with small triangles, which we couldn't do this. But I'd advise checking it out for your game. So what we actually ended up with SMAA. This is just temporarily stabilized, and we had a normal depth and luma predicated thresholding. So for the temporal supersampling, so this is based on work done for Killzone Shadowfall. So what we're going to do, this is 2 times supersampling. So we're going to use the current frame and the previous frame for our 2 samples. The previous frame sample is valid, only valid if the motion flow between frames n and n-1 is coherent, and also the color flow between frames n and n-2 is coherent. So we need to look at those 2 frames so they have the same subpixel jitter. That's going to prevent flickering. Except that we didn't actually do the frame n-2 stuff for Far Cry 4, and you can see some flickering present in the game. And thanks for those who already pointed out to me this GDC. So again, what are we going to do? So let's go over these metrics again. So if we have this geometric metric, which is looking at our motion buffer to make sure that we kind of stick with the same geometry. We interpolate between the same geometric objects. So interpolating from our n-1 to our n sample, the motion ends up being incoherent. And we're still going to do some kind of color metric on our the n-1 sample. So we're going to look at the color bounding box, about 3 by 3 neighborhood around our sample. If it's close to the mean, we take no new information. If it's close to the min and max, we think we have new information, we want to accumulate that in. If it's outside this window, then we think it's probably a fluctuation, we should get rid of it. And just to visualize that, this gives a good graph of how we're actually doing things. Hopefully that kind of makes a bit more sense with the visual. So we accept things around the min and the max of these peaks. It's actually worth looking at. We didn't actually use the mean at the end. We actually used the center of the pixels. So also, it's worth checking out Brian Karras' talk at SIGGRAPH last year as well, because he went loads of things on these acceptance metrics. So I definitely worth checking that out. So what we're going to do, we need to look at what samples we're going to use, what sample pattern we're going to use to maximize our 2 samples to get the best image out. So there's various sample patterns we can try. Let's take a look at what they are. Well, obviously, just for a one-time centroid, well, we're going to get some aliasing, and you can see kind of the edge there. A standard one, if you kind of 2 times MSAA, is your 2 times rotated grid. Well, it gets a bit better. You have actually some form of anti-aliasing there, but it's not great. We could do 2 times QUINCUNX. Now, QUINCUNX is interesting because it optimizes pattern by kind of sharing kind of corner samples between various pixels. So you have kind of 3 unique rows, 3 unique columns. But of course, this does introduce a 0.5 radius blur. Or we could look at doing something like 4 times rotated grid. Again, that should be 4 times samples, though. We can't really afford that. But it does give a better looking result. But there is a better pattern, and that's actually this thing called a flip quad. So it kind of combines these ideas in the 4 times rotated grid and also your kind of QUINCUNX pattern. So what happens, you have 4 unique rows, you have 4 unique columns, and it does also, like QUINCUNX, have this kind of 0.5 pixel blur, but you can actually recover that in post-processing with an unsharp mask. So it's actually going to be okay. Actually, you just do some comparison of actually some images. Well, it looks kind of as if like the flip quad is looking pretty as good as the 4 times rotated grid. And if we look at some kind of studies, it kind of turns out that actually flip quad is probably the best of them all, out of all the things we looked at. So let's go with that. So how is that going to work? What we need to do, we need to split the pattern in half. So on frame A, we're going to look at samples, say, 0 and 1, 2 and 3. And on frame B, we're going to look at the red 0, 1, 2, and 3. And for, say, for pixel 0, then, all we need to do is average your 0, 1 in blue and your 0, 2 in red, and that's going to give us our kind of a super sampled image. There are obviously some tricks with this. It doesn't work out quite as easy as you hope, because what you need to do, you actually need to interpret your UVs at sample positions. You can just use some HLSL interpolator modifiers. Of course, then you have the second problem where you have incorrect derivative calculations because your spatial distances between the rasterization samples differ. And that causes some quite bad problems because let's look at, say, frame A. Well, this is rendered with the correct MIP. And then what happens when we render with frame B, the DDX, DDY changes, and we get this over-sharpened MIP. And obviously, if we're going to blend between those two, well, we're going to have a few issues. So what do we do? Well, we actually just need to, we could do a few things. We could do some MIP blob bias between frames. Seems a bit tricky. We could obviously try to do things manually ourselves, but that's going to be expensive and a bit of a pain. Actually, the thing we can just do is actually just reorder our samples and to make sure that these derivatives match. And it turns out that's pretty straightforward to do, and it works pretty well. So this is the same image as before. Frame A still looks great. Haven't changed anything there. But for frame B, now everything looks pretty much the same as frame A, and that's great. Now, so the temporal anti-aliasing. So we actually temporally stabilize like a load of our buffers. It takes up loads of memory. That's cool. We've got it all on next gen, right? But it actually really gives a really good image quality. So we look at the final frame buffer, the SMA, our screen space bent cones, motion vectors, bloom. They're all temporally stabilized. So we have this history exponential buffer. And what we need to do is we need to amortize sudden visual changes, so to make sure we only accumulate new important data into it. We actually use the same acceptance metrics I just talked about for the temporal supersampling. So your geometric metric to compare whether the motion vectors are the same, our color metric to compare if the colors were in the same bounding box. So now we're doing this not only for our n-1 frame, but we're going to do it separately to our full history buffer. You might need to tweak those values separately, though, might get some good different results. However, after all this, we're going to lose a bit of detail. We need some wider and kind of more complicated kind of downsampling kernel. And also we have this kind of half-pixel blur from flip quad. Turns out this is pretty okay, actually. We just need to approximate a 4-tap sync kernel by doing a half-pixel blur. Hey, we've already done that with a flip quad. And we actually need to do a half-pixel radius unsharp masking as well. And then to match our super sampled resolution, because now our resolution is a lot higher than what it initially was, we just need to do a MIP bias on all textures. And overall, we have then some really high quality anti-aliasing, and actually the performance is really, really good. SMA is a millisecond, and look at our kind of temporal flip quad plus the temporal anti-aliasing takes about 0.65. And combine that with our unsharp mask as well, we've got 2 milliseconds then for pretty much for all our anti-aliasing. If we managed to do the coverage reconstruction anti-aliasing, we'd probably get a little bit back off that. But again, something to look at for the future. So what's the conclusions going to come to? Well, first of all, let's show you a bit of a typical performance of a typical Far Cry scene. It's awesome doing a cross-gen game sometimes because this is well in frame. Thank you to all the artists who made good data. So, as I said, the anti-aliasing is 2 milliseconds, about 3 milliseconds of post-processing. G-buffer is obviously the most expensive pass, followed up by lighting. And there's a few miscellaneous things in there as well. That's just our tree simulation and various kind of buffer copying. So, for Far Cry 4, we managed to make some significant rendering improvements to our engine whilst maintaining a last-gen build. We added some anisotropy metallic materials. We added some higher fidelity sky occlusion and some indirect lighting. We added a whole new vegetation system. And finally, we built a new anti-aliasing algorithm that to give us some high quality image quality at the end. Really, thanks to really everyone on the Far Cry 4 team, but especially kind of these guys who worked on things like mentioned in the presentation. A special thanks to Stephen Hill for all the conversations we've had about ACU and Far Cry 4, and to Julien Merceron as well for being the GDC advisor. I have a lot of references. Please check them out. They're all actually pretty good. They're worth your time. And does anyone have any questions? No one? Okay, you can come and talk to me afterwards if you need. Thanks again for coming, everyone.